Hello, in this video we are going to discuss moments. What is a moment? Well, the moments of a force is the measure of the tendency of the force to rotate the body in which it acts. So it's a lot like torque. The force applied to drive the bolt produces a measurable moment, and the wrench rotates about the axis of the bolt. When I put a force here, it's going to cause it to want to turn or rotate. That's how we know we have a moment. We've created a moment. Let's consider the terminology that we need to understand in order to be able to calculate moments. First of all, I'm going to apply a force here. We're going to denote that with an F, the variable F. The next thing we need to consider is the pivot point. It's going to pivot about the middle here, and so we want to also know the distance from the pivot point to the force. It's really important here that you understand the distance D we're interested in is the perpendicular distance. So from the force, we need to have a perpendicular distance. Let's consider the moments formula. How do we calculate a moment? Again, we need to go back and think way back to the beginning of school when we first started our talk and we were talking about work. We had work is force times distance. So that's the same thing for moments. We're going to multiply the distance from the pivot point to the force times the amount of force that we're applying. And again, very important, you need to write this in your notebook, we're interested in a perpendicular distance between the pivot point and the force. And I'll show you some examples of what I mean. This is how we measure moments in foot-pounds for English customary system, because we measure force in pounds of force and we measure distance in feet. Or for the International Standard System, we would measure force in newtons. We would measure distance in meters. When you multiply force times distance, you get a newton meter. This is going to be important because we're going to need to do some conversions for our moment calculations. Rotation direction is very important. So we just talked about having a scalar quantity versus a vector quantity. Moments are a vector quantity because our rotation is important. In order to add moments, we need to know if the direction is clockwise, denoted CW, or counterclockwise, we denote CCW. If your motion is counterclockwise, then the moment is considered to be positive. If your moment is considered clockwise, then we consider it as a negative moment. We use the right-hand rule to help us with this. Curl your fingers to match the direction of the rotation, and if your thumb is pointing up or towards you, then it's a positive moment. If your finger is pointing down or away from you, it's a negative moment. You might want to pause the video and write this down. For example, if the rotation is going this way, I'm going to pull my fingers in that rotation, and when I do that, my thumb is pointing up, so I have a positive moment. Let me show you a couple more because this 2D representation is kind of hard. So by the right-hand rule, when I push on this wrench, then my motion is this way. So I'm going to curl my fingers to go in the direction of the rotation, and when I do, my thumb is pointing towards me. So this means I have a positive moment. By the right-hand rule, now consider this example. If I make my fingers go in the same direction as the rotation of the wrench, then I'm rotating my fingers around, and now my thumb is pointing away from me. When your thumb points away from you, it's a negative moment. So let's do a couple of, let's do a couple of calculations to calculate the moment. Again, this is just trying to consider how much work is being done. Work is force times distance, so to calculate a moment, we're going to do the force being applied times the perpendicular distance. Again, I showed you that the thinking back to the right-hand rule, If I push the force on this wrench right here, it's going to cause my wrench to want to rotate in this direction, which is clockwise, and so I'm going to have a negative moment. But as I showed you in the chart that showed what units we use for moment calculations, we answer in foot-pounds for the English system, so I need to convert my 9 inches to feet. So to do that, I'm going to do 9 inches divided by 12 inches in a foot, and that gets me 0.75 feet. To find the moment, I'm going to multiply the force times the distance, and then I have to assign whether it's positive or negative, and I've drawn this arrow to denote the rotation. When I push, the rotation is when I go in this direction, and I put a negative here. It's going to be really important that you label your drawings with this so that you know if you want a positive or negative moment. So because I know the moment is negative, I'm just putting a negative symbol in front of the moment. Multiply that out, and I get 15 foot-pounds for the moment. And the negative is in front just to show me that I have 15 foot-pounds in a clockwise direction. We don't actually have a negative amount. That's for direction. Okay, let's consider a longer wrench. What's going to happen to my moment? So I still have 20 pounds of force being applied here, but now my length of my wrench is going to be 1 foot. So, to find the moment, we need to multiply the force times the distance. I need my distance to be in feet, and it is. So on this one, I can simply do 20 times 1, but I need to consider the direction of the rotation, which is clockwise. So I've drawn an arrow to show it will go this way, and I've noted that a clockwise rotation is a negative moment. So I've assigned a negative to my calculation. So now I'm going to have 20 foot-pounds for my moment. So remember from our discussion of torque, this is why we have cheater bars and things. When you're having a hard time changing, getting a bolt loose or changing the tire on your car, we'll often put a pipe or something to make this longer, because the longer the distance, the higher the moment or the more torque, and then the less work you have to do. Let's consider an L-shaped wrench. I know you haven't really seen one, but I need to use this example to show you what I mean by a perpendicular distance. Notice right now, if I look at this distance, it is parallel to the way that I'm exerting my force. So I do not want to multiply 20 times 1. These two are parallel. I need to know this distance right here, because this is the distance that is perpendicular to my pivot point. So I want this distance, which is 3 inches. So to calculate the moment, I need to convert my distance from inches to feet, so 3 divided by 12 is 0.25 feet. To calculate the moment, I am going to multiply the distance times the force, and again, I always have to consider the direction. When I push on this, it's going to cause this to rotate in a clockwise direction, which I've noted here with my arrow, so that's a negative moment. I've inserted a negative sign in front of my answer for my moment. This means we have 5 foot-pounds of the moment in a clockwise direction. Let's go a little bit crazier. What if I have a Z-shaped wrench? Okay, again, not highly likely you'll ever see or use one of these, but I need to use it to make sure we understand the perpendicular distance idea. So I'm going to exert 20 pounds of force on the wrench at this point. So this is no longer the distance that I need that we use, because this distance is parallel to my force. I'm going to want the total distance from the pivot point to the force, and the distance and the force need to be perpendicular to each other. So to calculate the moment, I'm going to want to use the distance 18 inches. I need to convert those 18 inches to feet by adding the 8 inches here, and the 10 inches here. 18 inches divided by 12 is 1.5 feet. To calculate the moment, I do the distance times the force. It's that easy. 20 pounds of force being exerted at 1.5 feet away makes 30 foot-pounds for my moment. And then I have to consider, when I push here, what direction is this going to want to rotate? counterclockwise, and that's a negative moment, so I assign a negative to my answer. Now let's consider a wheel and axle. What's going to happen? What's the moment when I turn this wheel and axle by pushing with 100 newtons of force straight down? Okay, so again, to find a moment, I need to do the perpendicular distance times the force. So my distance from the pivot point here in the center to the force is 50 centimeters. For the international standard of measurement for moments, we need newtons and meters, so I've converted my 50 centimeters to a meter. To find the moment, I'm going to multiply my half of a meter times my 20 pounds of force, and then I need to consider when I exert a force here, what direction is this wheel going to want to spin? It's going to want to spin counterclockwise. Counterclockwise direction, I'm denoting an arrow of this way it's going to spin, and then I write a plus because when I calculate my moment at 50 Newton meters, I want to have a positive answer because I've got counterclockwise rotation. That's a positive moment. Now, what should happen if I did not exert my force straight down? What if I am actually pulling off to the side here? Then I'm going to need to calculate my forces, break this into my component vectors. We've done this in the last day or two as well. And I need to know how much of that force is acting straight down. I'm not really interested in the x component because if I pull straight out, is this wheel going to want to rotate if I'm pulling on it? No, I think not. So I'm not interested in the x coordinate. Only interested in the y because that's what's going to cause a moment. That's going to be what causes this wheel to want to rotate, is this force acting straight down. So, first thing I need to do is find the y component of this vector. I have a 50-degree angle here, and so I can transfer that to this triangle here with my vector components by alternate interior angles are congruent. So if this angle is 50, this angle is 50. To find my force in the y direction, I need to do the magnitude times the sine of 50. So 100 times the sine of 50 degrees, and again, make sure your calculator is in degree mode because radians will give you an answer, but it will be wrong. When I multiply that out, I realize that the force that's acting straight down is 76.6 newtons. So I'm going to put that into my moments formula. After I convert my distance of 50 centimeters to meters, I can find the moment by multiplying 0.5 meters times 76.6 newtons to give me a total moment of 38 Newton meters. Again, it's a vector quantity, so I need to consider the direction, and I need to consider when I push on this wheel, it's going to make it want to spin counterclockwise. Counterclockwise is a positive rotation, so this is a positive moment. This concludes part 1 of moments. We are going to give you an opportunity to investigate moments a little bit further before we start doing all the crazy calculations for statics. So at this time, please ask your teacher to direct you to the equipment and the materials for the Moments Lab. Thank you for listening and enjoy the lab.